Hello and welcome to the first part of Lecture 22. Here we're going to be covering Section 10.3 from Young 14th edition. The topic is rolling motion. This lecture is designed to get further practice with rotational motion, specifically rotational motion combined with translational motion. There are going to be a number of considerations that we're going to have to carefully make when we talk about rolling motion. We're going to come at this from a few different points of view, including energy, torque, and Newton's second law in rotation, as well as thinking about relative velocities along a rotating object that's translating through space, or in particular, translating relative to the ground. So let's get into our definitions here, kind of thinking about what we're talking about, and then of course look at some good examples. Okay, so the big idea is rolling motion as a standalone topic in an introductory physics class is an inclusion of stuff that we would have seen in the conservation of energy chapter, but also something new. And the something new is the idea of slipping or rolling with slipping. Okay? So when you talk about slipping in the context of rolling motion, what we're talking about is rolling with slipping. So this is rolling motion with slipping. Okay? So that's what slipping is short for. All right, so let's unpack that a little bit. So first of all, pure rolling motion would be rolling without slipping. Okay, so pure rolling is rolling without slipping. Okay, and in that case, in the pure rolling case, we have that the velocity of the center of mass of the translating object, so v com, equals omega r, okay? Where omega is the angular velocity of the rotating object, r is just the radius of the rotating object, and again, v is the translational velocity of the center of mass of the rolling object. And furthermore, that would be equal to v of a point along the perimeter. So I'll call this V perimeter. Okay, we'll come back to this idea, but simply to put it into another picture, to risk being repetitive with the pictures below, but still worth it, we will have a rolling object. Okay, so again, pure rolling tells us that we have some angular velocity. So we have some omega, okay? Omega would be coming out of the board at us in this case. If you take your right hand, or sorry, be going into the board. If you take your right hand, you curl it. We know that we would have an omega going in to the board like so. Okay, with that notation representing a vector that's going into the board. Okay. Then we would have a translational velocity of the center of mass that would look something like this. Okay, so this would just be v com. All right. Now, again, more on this in just a minute. That would be relative to the ground, right? So that's the translational velocity of the center of mass of the rolling object relative to the ground. That is taking the rolling object and simplifying it to a particle and looking at that particle's translational motion relative to a fixed reference frame, the ground, which is what we always do, in fact, when we talk about translational velocities. Okay? But that then translational velocity would be equal to the velocity of the perimeter of the rotating object relative to its own center. Okay, so then we'd have any number of velocity vectors we could draw along the perimeter. And I'll draw one such vector. Okay, so that one would also have the same value. This would be v perimeter, right, as a vector. And its magnitude would equal v com. Obviously, its direction absolutely need not be equal, okay? But its magnitude is. So that's pure rolling motion. It's something we've kind of touched on briefly, okay? And it's something we'll see in this section in a more direct light, but it's not the only type of rolling motion. And in fact, I would say it is not the type of rolling motion that is the most interesting, the most complicated, maybe the type of rolling motion that will be the most memorable is in fact rolling with slipping. But what is that? Okay? All right, so then we have, on the other hand, rolling with slipping is not pure rolling. So any rolling that is not pure rolling would be rolling with slipping. And in that case, v com, the translational velocity of the center of mass, in magnitude, does not equal omega r. Why might that be? Well, this could be an object that has a translational velocity where v com is larger than omega r or smaller. Okay? And we'll talk about both of those cases. And in either of those cases, then what's going to be happening is the object is going to be transitioning to rolling with slipping. Oh, misspoke. It's going to be transitioning to rolling without slipping. So rolling with slipping is always transient. It's always a transitional type of motion that will eventually lead to pure rolling. So all rolling with slipping can, because of course it could, the rolling object could come to a stop, right, or reach the end of the track, but given enough distance and time, it will transition to pure rolling. Okay, so why is that? Why would it transition to pure rolling? Because the either excess angular velocity, making omega r larger than v com, or the excess translational velocity, making v com larger than omega r, that excess velocity in the form of excess kinetic or rotational, excess translational kinetic or rotational kinetic energy will eventually get dissipated by a friction force. Why do we know there's a friction force at play? Because you can never get any type of rolling without friction. So an important and easily overlooked concept about rolling is not possible without friction. So rolling of any kind is not possible without friction. Okay? So one idea that builds directly off that is if we have sufficient friction, then we can have pure rolling. Okay? So sufficient friction will lead to pure rolling. Leads to pure rolling. Okay? So what is sufficient friction? Well, that means that we need to have the object decelerate until the friction balances out the mass times acceleration, or moment of inertia times angular acceleration. And when the friction balances out, then pure rolling will begin. Okay? That's the transition, the transient nature of rolling with slipping that I just mentioned. But that does beg the question, well, does the friction then continue to slow down the rolling object? No. Once an object begins to roll purely, it no longer is decelerated by friction. Well, how is that possible? It's possible because the point of contact, and I'll label this in the figure below, the point of contact with the rolling object and the ground is not translating. That single point of contact is only moving in the vertical direction relative to the ground. There is no parallel movement relative to the ground. Thus, there is no possibility for friction to do any work, because work is, of course, force times distance, and when distance is zero, work is zero as well. The work done by friction is zero. The change in kinetic energy of the rolling object cannot change due to the work kinetic energy theorem. So, what does this mean? Well, it means that we're talking about an idealization here. We're talking about an object that is so perfectly rigid that the point of contact between it and the ground is truly just that, a single point. It has no length, okay? Real objects have contact areas with the ground, so there is always side-to-side motion, so there is always a removal of kinetic energy due to friction, okay? But here we have the idea that pure rolling is actually an end state. Once an object begins to purely roll, it will continue to purely roll because friction will no longer be able to do work. Okay, that's a weird idea, right? But that's the simplification or a consequence of the simplification we make. Okay, we still have a good model here of the physical world. Like all models, it's not perfect, but it does represent it well as long as you understand that that one caveat is odd. Okay, so then pure rolling is a final state because friction does no work when pure rolling begins. We'll say when pure rolling state is met, but also just begins. Looking for the right word there. Okay, so two types of rolling, some important details about what we mean by pure rolling. Let's take a look at the figures below and make sure we can continue to make sense of this. Okay. So looking at the figures below, there's a couple of things that I'm kind of calling to your attention. And this is under the heading of frame of reference for rolling, relative velocity. Okay? So the first set of pictures, A, B, and C, are meant to show that we have a traditional relative velocity formula to relate our two reference frames. Our two reference frames are the reference frame of the ground and the reference frame of the center of mass of the rolling object. Okay? So I'm going to go ahead and write below these figures the appropriate equations with subscripts to clearly show that we are talking about a relative velocity formula. Okay, so the first figure here shows pure rotation. Okay, well, pure rotation gives us the idea that the velocity of a point, such as P or T, relative to the ground, is going to relative to the center of mass, is shown in the figure. So this would be the velocity of a point relative to com. Okay, so there's our velocity, and I'll write this as a scalar equation just with the appropriate subscripts, as we do with our relative velocity formulas. Our next equation is the velocity of the com relative to the ground. So this is the velocity of the center of mass itself relative to the ground. Okay, well, if we think of our subscripts, because we have a V A relative to B, V B relative to C, so then if we want to get V of A relative to C, then we'd simply squish in the center of mass and it won't show up anymore. And so then the final effect will be V of a point relative to the ground. Okay, so that's the relative velocity formula. That's our two reference frames. Okay, so we have one fixed reference frame, the center of mass, and we have another fixed reference frame, the ground. So what actually happens when we put this into practice? Well, let's think about 2 points, point T and point P. All right, so the top and then the contact point. So we'll have T and P. Okay, so for T, what is the result that we get? Well, we'd have the velocity of the point relative to the center of mass would just be V. We'll just call that V, okay? Then we're going to have, in the next one, the velocity of the center of mass relative to the ground, okay? Well, that is going to be V as well. It's always V. And so that means that the velocity of point T relative to the ground is 2V. So it means that the top of the wheel relative to the ground is moving at a velocity that is exactly 2 times the magnitude of the velocity of the center of mass relative to the ground. Well, that makes sense, doesn't it? Okay. And if we do the same thing for point P, we have negative V, okay, because it points in the backwards direction, plus positive V, because the velocity of the center of mass relative to the ground is always just going to be V. And that gives us, of course, 0. And the result 0 tells us that the velocity of that point, the point in contact with the ground, is actually 0 relative to the ground itself. And that is exactly the point I was trying to make about pure rolling. the idea that pure rolling means that the contact point does not move relative to the ground. Okay, so up here I'll add the word pure, because this is pure rolling motion. Okay, and then over here I'll add the description that this shows that point P does not move, think translate, relative to the ground. Okay? Make sure you wrap your head around that idea, right? That is a consequence of our ideal rolling motion. It would require a perfectly rigid object. Okay? Obviously, I could do this for one last point. I won't do it. I won't write it out at least. But if I was to think about point 0, well, the velocity of point 0 relative to the center of mass is 0. The velocity of point 0 relative to the ground is just v. And so then we get that the velocity of the center of mass relative to the ground, well, it's just itself. It's the velocity of the center of mass relative to the ground. It's v. Okay? So it'd be 3 points, the top, the middle, well, the center, and the bottom. Okay? Now, that means that really there's two main ideas that you need to be thinking about and processing and being ready to work with. One is this relative velocity idea, some of these assumptions and simplifications of what pure rolling means. Okay? That's something you need to spend some time with and make sure you understand. But simultaneously, you also need to be thinking about the fact that pure rolling is an end state, and it's interesting and perhaps difficult to work with. But that's not it. That's not the whole story. There's also this transition up to that end state, that idea of rolling with slipping. And that's going to require us to solve some basically kinematic equations, to set up a force diagram and then solve a kinematic equation to get to that final state. And so that's the other main idea, is how do you get there? How do we actually solve for a transition from slipping to pure rolling? Well, it's really going to take the form of using these two equations here. The two that are our first two key formulas. Notice I list these as Vcom equals omega r for rolling without slipping, and Acom equals alpha r for rolling without slipping. So these are the conditions that are reached when slipping ends. Conditions that are met when slipping ends. Okay, because when slipping ends, pure rolling begins, and we are done with the with that side of the kinematics. Okay, we're done with that form of acceleration. Okay, and in fact, we're done with the particular. In many cases, we would get to a state where we'd be done with all acceleration, because then we would just hit a constant velocity case. We need not be, however. We could have, certainly in the last example shows us, we could have a case where we're done with slipping, so we're done with one form of acceleration, but the center of mass is still accelerating relative to the ground because there's a slope involved, for example. Okay? So even though friction isn't doing work, gravity does continue to do work. But what it always represents, it's the end of friction doing work. Okay? So it's when slipping ends, and we'll say, and friction does no more work, because that's such an important idea that is so easily overlooked. Okay? Friction only does work up until pure rolling begins. I know, I've said it a lot, but it's worth repeating. This last diagram, by the way, this one I will refer to in one of our examples. This is just showing this idea of using relative velocity, not just for points P or T, 0, and P, but for any point. Right, so all of these particular vectors would be a result of using the relative velocity formula for individual points along, they say, the rim of a wheel in this case. And in doing so, we're really getting a case where we're going to have a vector. We can find its particular angle, its particular magnitude. Notice that the vectors down below or near contact point P are much smaller. That's because, of course, they're approaching 0. And then the vectors up near point T are much larger because they're approaching 2v in magnitude. Right? But we can find any of their exact values just knowing their location. Okay, and then putting in the appropriate, because essentially we'll be putting in the appropriate components of the velocities, because we'll have to split the relative velocity formula into two components, x and y, and then we can easily find the effects of both the components. Okay, all right, and then you use the Pythagorean theorem to wrap things up. The last formula is a bit of a repeat. This would have been a formula that would be well suited to our conservation of energy chapter or set of lecture notes. But it's just kind of important to put it here because we're going to be using it a lot. And this is just showing that the kinetic energy of a rolling object is composed of two parts, a rotational component and a translational component. All right, so this is the total kinetic energy of a rotating object. All right, and so this is then just its rotating kinetic energy, and then this is a translating kinetic energy. So notice that a couple of things here. One is that when we look at this, we can if we have a purely rolling object, then we can do a substitution, and these become like terms. Okay, so they would always combine together. They would not be like terms in any case where there's not pure rolling. Okay, so we'll say note the two energy terms can be combined for pure rolling. And since that's kind of a confusing idea, I'll just do a quick example of that. So e.g., for purely rolling cylinder, let's bring this over here. We would have 1/2 times 1/2 mr squared. That's just the the moment of inertia of a cylinder. Omega would then become v over r squared. Over here we'd have 1/2 mv squared. Okay, because remember this is v com, right? Because this v right here is v com. I just dropped the subscript, right? So when we see then that those are both like terms. They have the same units. They're an m and a v squared. We could have substituted the v in terms of omega and had also a similar expression. Okay, but this one, we'll do it this way to simplify things. And so let's cancel out our r's. Okay, and so then we would get a result that our energy would be 1/4 mv squared plus 1/2 mv squared. Notice that the translational kinetic energy is twice the size of the rotational kinetic energy for a cylinder. For any object, I'm just going to state this, for any object where the rotating axis is the same length as the moment of inertia axis, so in other words, anything that's not like a yo-yo, nothing with any excess matter or excess kind of distribution of mass that's further away from the rotational axis. Again, think of yo-yo, right? Because it's got that small spindle inside and then all the excess mass around the sides. Well, for any object that isn't like that, so an object like a rolling cylinder or a rolling ball, in that case, all those traditional rolling objects will always have a kinetic energy for translation that is larger than its rotation kinetic energy, right? So in the case of the cylinder, it's twice as large, but it'll always be larger. Okay, quite interesting there, isn't it? And so once we find the total energy, though, in this case, we would have 3/4 mv squared. Okay, so that's that would be the total kinetic energy of a rolling cylinder as long as it's purely rolling. Okay. Hopefully that looks good, and it does make sense that it's bigger than just a translating cylinder, right? Because a translating cylinder doesn't have that extra motion. It's not moving about its own center. Okay. So I'm going to do one concept question, and then we'll finish up this half of the lecture, and then come back for some more examples. I think I'll probably put all the examples in one video, but we'll see how that works out. So let's just look at this first example briefly. This is one I just put in here because it's I think it kind of calls attention to what rolling can mean depending on forces, and so it's a kind of a good precursor to some of the things we're going to see in terms of rolling and slipping and so on. So here we have a car that is increasing. So we say, okay, let me read the whole thing. So when the speed of a rear drive car is increasing on a horizontal road, what is the direction of the friction force acting on the rear tires and the front tires? So you might intuitively say, oh, well, of course they're going to be the same. We can't have friction operating in opposite directions. But in fact, we do have friction operating in opposite directions because the friction is doing different things on the different set of tires. Because this is not a four-wheel drive vehicle. The tires in the front are passive, okay? Well, so what does that mean? What's the consequence of that? Now, for the concept question here, there's no importance in terms of differentiating between rolling without slipping or purely rolling. The result would be the same. So don't worry about that. But if I was to think about the translational acceleration of some point, or specifically the center of mass of our car, but I'll draw it up here because that's where the velocity is drawn. Well, we know that the acceleration would have to be in the same direction as the velocity because we have a car that's speeding up, right? We were told that. Okay, so increasing. Well, if that's the case, if there's an increasing acceleration, that means that the friction on the rear tires must point in the same direction as the acceleration because there's no other force that would actually be propelling the car forward. There is presumably drag acting against the car, but there must be a larger friction force pushing the car forward. That is literally the only reaction force that is driving this car. Okay, it's not rolling down a hill, it's on flat ground. So then we can say that the friction force on the rear tires points forward. And we know it does that because we have a vector equation that says that the friction force vector equals the mass times acceleration vector. And if I was to draw that in the figure, it would look something like this. So it'd simply be a little vector pointing forward. And again, it's just pointing in the same direction as the acceleration vector. Right? So that would be the friction force vector. Meanwhile, what about the back, right? Why do I claim that the back would have the opposite result? Well, the friction force points backwards on the rear tires because we know that the rear tires must be accelerating. I mean, I said rear tires, but I meant the front tires. The front tires must be accelerating in the angular sense. They have to be speeding up, right? So if the car, say, started from rest, those passive front tires initially would be at rest, and then they have to start speeding up. They have to start spinning faster and faster. Well, in order to spin faster and faster, there must be a torque, and that torque has to point in the same direction as the angular acceleration vector, which would have to point in the same direction as the angular velocity vector, which if you curl your fingers in the direction of this red vector here, you see that your thumb points out of the screen, right? It tells you which way it points. So in summary, I'll just write the result here. The friction force points backwards from torque equals I alpha, okay? Again, torque out of the page, alpha out of the page, which if we were to expand the torque equation, it would simply be friction force times radius equals I alpha, okay? And only a force that points backwards would create, using the right-hand rule, would create torque in the same direction of alpha in the same direction as omega, which we know we need because we need that tire to be spinning faster and faster, okay? So confirm that with the right-hand rule for yourself so that you believe me. Okay? So that would be the friction on the front tires, like so. All right. So interesting result there, I think, okay? So again, back